excited to introduce our last speaker of the summer school, Leonardo, who is doing some really exciting work on diffusion model for climate and fluid flows. Leonardo is a research scientist at Google. And yeah, so this should be a super fun talk to conclude and connect back to some of the topics we covered on Monday.
Oh, thank you, Ben. I mean, I will see how does this work, or we'll see. Hopefully, I mean, I normally speak fairly loudly, so at least people will be able to hear me here. Well, thank you, Ben, for the invitation. It's really great to be back here. I used to be a postdoc in the building 50A, so I just went there to say hello to all friends, and I see a couple of old friends here too. So this is a pretty hard task. You have to finish with something that is looks appealing, and it's most likely this is the first and the last talk that normally you remember summer schools. So hopefully you will get a good impression for this one. Just a quick question: how many machine learning scientists do you have here? Okay, how many engineers? Applied math? Oh, very little. Okay, that's weird. I mean, normally everyone will jump in apply math, engineer. Physicist, okay, a chemist, geoscientist, or atmospheric scientist. Okay, very good amount. So I will try to make this as very general. So I wasn't able to talk what I wanted to talk because the manager that was supposed to approve was in holidays. So I will have something like this. So the first thing I want to acknowledge, we're a very small team in Google Research. But we leverage a lot of collaborations across the different areas. So we are a bunch of meteorologists, applied math, climate scientists, computational physicists, and computer scientists. And I would argue that for now, I mean, in the current times, to really do research, you have to have these very big multidisciplinary teams. So I will try to start with like a small motivation. So I usually use this slide when I travel, when I fly. But I just drove from Mountain View today, so I mean, it doesn't really hold. But in general, like, I mean, again, you want to, every time that you travel, you want to do it be fast, secure, although Boeing is not doing a very good job at that right now, and somehow be efficient. But like how we got here, and the point I want to make is like, this is really an evolution of human ingenuity, how we got to get this big metal burst to fly. So if you go back in the day, in the mid 1800s, you will see like the modus operandi was very labor intensive. So basically, you build a plane that you thought that it would fly, you try to fly it, you crash it. If you survive, and if you're lucky enough and you have enough grit to continue, you build another plane and you repeat, and you go over and over. And you can see here, this is people were really have a lot of motivation, right? So you have 14B, so this guy tried 14 times until he gave up. 21. This one was like Jean-Marie Le Bris, after the 3, just was it's enough, no more. But then if you go back, so you go forward like 50 years, you will start to see that people are now understood like Navier-Stokes, and people start to doing this airplane design in a more principled way. So something that I didn't know before writing this slide like a year ago is that one of the main advantages of the Wright brothers that they basically led to build something that actually fly is that they actually use a wind tunnel. So they have this kind of little thing here that is kind of the wind tunnel you will be in like in high school, and they have a little window here, and they could add different like small models or wings and see if the drag can come back and down. And some people claim that this is basically what really led them to be able to build something that actually fly. And of course, then this becomes even bigger, right? Like in the space race, NASA have like these gigantic like wind tunnels to evaluate the drag and the coefficient of the airplanes. But then if you go now, everything is on a computer. Why? Because even though this is much more efficient than just building, crashing, it still is time consuming. You have to build these big models, and you want to do it faster. So the point here is like, can we do everything on a computer? And the answer is yes, to a degree. So now everything that is a new airplane is basically simulated extensively on a computer and for communication, for aerodynamics. But still challenges remain. sorry, I forgot that it's a slide here. So now basically all these computations become ubiquitous. So the market for simulation software is around like a 50 billion, I think it's 25 billions now. It's supposed to go to like almost 40 billions in 2033. And this is basically everywhere. So you take a look at your phone, the camera was done in a simulation, the microchip was done in with a lithography simulation, like this one in the middle. And you have an electric car that I saw several here. The battery have to be simulated, and the motors are being simulated. So everything basically runs through simulations, and this has make things more like cheaper, and it really make the design cycles much shorter. But it still many things remains. Now, we want to have high fidelity, but normally the cost increases quite dramatically as you increase the fidelity. The second one is that you don't want to only have one simulation. You want to have a plethora of them. Why? Because building these things, for example, you have uncertainties in the materials. You have uncertainty, I don't know, like a bolt can be moved to the left, to the right. You have uncertainties on measurements and so on. So you need to be able to quantify that uncertainty. And that normally requires to repeat the simulations many, many, many times to capture posterior. And the second one, if you want to do optimal design, you also want to basically survey or summarize the design space as efficient as possible. So that's kind of that applications for that, but it's still these type of challenges permeate all the domains. So what I mostly will talk about today is things related to weather and climate. So you have these processes that have the same similar challenges, but in a complete different scale. So just want to give a little bit of history here. So back in the day, like 2022, like Louis Richardson have like this idea of having this the fantastic forecast factory. So you have this gigantic globe, you have a bunch of people observing the Earth at every point, and then you will have like a bunch of people like in algorithm rooms. At that time was really people that are doing like calculations by hand or using these rules. I don't know if you've seen like these like calculators or rules back in the day. I mean, my father at some point gave me his as an antique. Anyway, you have all these people do these computations, and that they will basically want to do is try to predict the weather for like 2 or 3 days. And this is basically the one kind of I mean, the Bible of like a numerical weather prediction. And this one, it was 1922. But the problem is like, it took almost 30 years to have the first very bad, completely unusable forecast. And you can see here people, so this is a picture of this. So you have an Enigma-based mainframe. So the same one that, well, a modification of the one that cracked the Nazi code. And then even in this case, you can see that you have multidisciplinary research. So you have von Neumann that is here, and you have Jules Charney here. That's the one that wrote the CO2 and climate scientific assessment, the first one in I think in the 70s. But why it took so long? And this is basically, I want to go back to the points like computation and efficiency is really key to the scientific endeavor, particularly for downstream applications. So if you go back to the 50s, the resolution was 250 kilometers. So basically, each pixel was very big. 1971, 200 kilometers. So this is basically Petaluma to Monterey. So I mean, it demonstrates your definition of the Bay Area. That is kind of the biggest you can have. Then in the 90s, Bay Area, 60 kilometers. 2006, 25 kilometers. So this is basically San Francisco County. And you can see the trend here. So every 20 years, basically, in 10 years, you reduce by half. And the best weather we have right now is 3 kilometers. This is experimental. So you can only run it, it's not operational. So operational, what I mean is like you try to produce forecasts every day. This is basically just like a proof of concept that NOAA launched this year. And then we hope that at the 35, you can get like 1 kilometer. And 1 kilometer is kind of the panacea. Like you're supposed to be able to capture clouds at that degree. So what does this mean in terms of, oh, there it is. So that means that if you go and you take a look at the skill, so this skill is basically the accuracy to a degree of your prediction. And different colors, you have the lead time or the time horizon. So forecast at 1 day, 3 days, November 3, 5, and 10 days. And normally 60% is useful. And you could see as the time increases, how better and better this simulation or this forecast is getting. And normally 60% is the one that you're supposed to be useful. You can predict something. So the point here is like, you get basically 1 day-ish per decade. Now, if you go after 2022, this becomes like a big impact. So basically in 4 years, you go much higher. So basically, you AI using machine learning methodologies basically surpass operational systems with a lot of caveats. I mean, we still need NOAA to actually get the data and basically get the data to feed this model. But it's still, I mean, in the last 4 or 5 years, it's been a revolution. It depends who you talk to in the how fast it is being increased. But still, even at that, we're not still at this level. So we're still around 25 kilometers. What we want to do is really go to 1 kilometer or more. So the point is like how we can use this to basically improve weather prediction even further. Now, this again has the same type of problems. Computational costs increase. Well, it depends how you quantify, but resolution normally increase to the 4th power because you have 3 dimensions and you have a CFL condition, so it becomes very expensive. You don't have one forecast. You have an ensemble forecast. This is particularly useful for tracking cyclones or hurricanes. You want to compute the probability of making landfall on the fly. I mean, on the fly, like every hour or so on. And we still have optimal designs in this case, particularly if you want to build like a resilient infrastructure. So how a hurricane is going to look, where you have to build your dam, and so on. So you still have the same type of challenges, but in a different context. Now, this is kind of the setup. Hopefully, you're not bored yet. So the result of the task will basically try to evangelize you or like try to sell you how these AI technologies, generative AI, can actually help in a different problems related to this weather and climate. Now, I'll just show you a bunch of like a reference here. I mean, I don't like to do this, but in general, I learned being in an industry that you want to show to your boss that you've been productive, so you can justify your salary. So just put it there. I mean, we're being productive to a degree. Okay. The other thing, like, I just want to. I mean, I think that you. I went through the slides of the other presenters. Like, you've been sold a bunch of like different demos, different code bases. So we'll try to sell you this one. So if you like JAX, we have like a framework that is. I mean, this is software design is always like a balancing act. You want something that is flexible enough so you can use it many times. You want something that is performant enough so you don't wait forever running your computation. And then you want something that actually other people can use. So we try to strike this balance. So we have these libraries, raw dynamics. It's very lightweight. You can manipulate them fairly quickly, fairly easily. It has enough bells and whistles, so you don't have to repeat your like a train loop every time. And everything that I mean, all these papers here, all are open source, and everything is basically spec somewhere there. So you want to take a look? Go ahead. If you have any comments, please let us know. Now, okay. So this is the outline. So given that it's a very, we'll most likely have lunch in like half an hour. I try to do some menu. So you have aperitif, apero, and you have like three dishes. I mean, I don't know. Perhaps you're used to more fancier restaurants and you have more. Also, just like just one like a burrito, and you only have one. Anyway, so let's start with the first one. So what we want to do at the end of the day is try to model dynamical systems. So fluids, even for like small like molecules, to all the way to weather and climate. You can squint a little bit and you will think this is a dynamical system. So here's simple. You have like an initial condition, and then you have an operator that basically you apply repeatedly and you get the next step. Now, sometimes you know the governing equations. So for example, you have Navier-Stokes. That is nice. So you can do tax as acceleration. Sometimes, if for example in weather and climate, you only know half of the equations. If you were to do this for like astrophysics, you know no equations or like very approximate ones. So you have all the range. How much noise do you want? Now, the typical learning task is, if it runs, I should have it. Okay, there's something moving there. So the main task is basically, what's your data? You have trajectories or simulations. And then the goal is basically try to have a model that mimics or learns the dynamics. And why we want this is basically to reduce the cost. And by the same time, you want to maintain the fidelity. So there's two ways that we'll discuss a bit later. So one is try to match the trajectories directly. And the other is like, well, that's too hard. Try to match the large scale spatial temporal patterns. And you will see in a moment when one and the others are more easier to do. Now, if you give this problem to a machine learning scientist, they will say, wow, but it's easier, right? It's just a video. Just run a video transformer there and we're fine, right? But you realize that your video transform becomes basically a nightmare. Why? You start, like, I don't know, you start walking on the beach and so on, and then, I don't know, a dinosaur appears, and then becomes things very chaotic. So this is basically similar to happen here. You have something that is very well behaved in fluids, and then becomes chaotic. And then it's very hard to approximate. Sorry, what's the next slide? Okay, so what happens, and this is basically what the same Lewis Richardson basically put this into a fairly poetic versions, like you have big wheels, have little wheels that fit on the velocity, little wheels have lesser wheels, and so on to viscosity. So basically what it means is like you have different resolutions and the scales interact. And I mean, this is kind of the less poetic translation that we all know. Physics can resolve when the scales are properly set up. Physics are not resolved. It's more at stake because we cannot resolve. And why is this issue? Is because you have a nonlinearity. So basically that makes interaction all the possible scales. So like, can we get rid of that, or can we basically be able to resolve without resolving? Now, so what is the cost here? So how we go from something that is cheap to compute, that is biased. So basically, what I mean with bias is like doesn't capture the full physics or the small scales, to something that actually captures the full physics. So one side is low fidelity that we call a bias simulation. This is cheap to compute. You can crank it up very easily. And then you have high fidelity simulation. I mean, this is just an example. You have finite volumes and a high accuracy spectral method solving. So how we bridge these gaps? Have something that is easy to compute, cheap, and something that is more expensive. And that's basically what we try to do, go from the left to the right. It will do differently. So this is kind of the main cartoon. You want to do this with weather and climate, which are much, much bigger and much more complex examples. So what are the methods? Again, this is generative AI for this coarse scale first grain modeling. And again, so basically what you want to do is based on these two things, try to have put like AI or ML methodology in the middle, squeeze it. Now, again, if you're a computer scientist, like, well, I mean, this is not that hard, right? I mean, you want to basically go to the left, that looks like a low resolution, to the right, that's high resolution. So this is well known. People have done it a long time, computer vision. So you have like a fuzzy cheetah in the left. You have a nice high resolution cheetah on the right. So let's try a model. Like, let's put these two things together and learn how to go from coarse to fine. This is people will call like supervised learning. The problem is that in many cases, there's a bias. So the one on the left is a climate simulation that's pretty standard now in climate sciences. And at the right, you have weather simulation that assimilates real data. So this is kind of the closest you can get to real weather without going to observations. And you can see there's something missing, right? I mean, for example, Katrina, for this particular date, is here, as it should be, but in the core simulation, it's not. Naturally, you can try to run many simulations, and you will never see a hurricane. Why? Because you have a bias. So basically, hurricanes, I mean, it's a complicated process, but when you run a low resolution, you cannot basically have these very convective, very strong cyclones. You don't see them because of the bias. And the other issue is that there's no correspondence. So basically, you see these different members. So this is called lens 2. There's a climate simulation that you have like 100 members. samples. And you can see that there's no correspondence. I mean, it is the same day simulation. I mean, the large scale, well, the hurricane is not there anywhere. But you see, like these elements here, they don't even correspond between them of two. So basically, you have images, but you don't have this score resolution, and this is the high resolution version. So you don't have this correspondence. Now, so basically, in this case, supervised learning is completely useless. Now, in a nutshell, what I want to say is that basically you have two goals in one task. So you want first correct the bias. So basically, make this thing looks more like this, and then add the resolution. So go from a low resolution to a high resolution. And I like this plot a little bit. So for example, you can see this is your bias one, and this is your unbiased Fourier spectra. And adding resolution, what it does is basically Fourier extrapolation. So you have certain Fourier signal, and then you add extra details at high frequencies. But in this case, if you go from biased and you try to add more Fourier information, they don't live in the same manifold. So if we go back to this question, it's like you have a cheetah and then you try to add resolution. If you try to super resolve a dog, it will try to force it to add spots to the dog because they're not. That is the model is learned to basically add spot to the cheetah. If you add a dog, will try to basically give you a Dalmatian or something like that. So, but you have to correct. So that's kind of the main point here. So you go from a bias, you unbias, and then you extend the Fourier components. And we have a paper on this in here. So how do we do this then? How do we do two operations in one step? So we go back to what people call like latent variable modeling. So what you do is say, well, let's suppose that something exists in the middle. You have a cloud of latent variables, which you leverage to go from y to x. So the first step will say, we don't want to just go from y to x directly. We don't know the correspondence, but instead what we want to do is be able to compute this conditional probability. So we want to sample from p of x. So knowing y, what are the possible x's that had correspondence? Or you can think like, what is the possible x's if you filter it and you don't sample, you obtain the y. So the main technique here that will permeate the rest of the talk is try to use this latent model. So basically you have some variable y prime, and then you write your expectation as basically going from y to y prime in here, and then going from 1 prime to x. Now, as you may realize, we make the problem harder because going from one to the other, it was fine. Now you have to integrate over all these possible latent variables that we have to define later. So the simplest way to here is like just instead of having a cloud, just basically just compact it to only one. So this is, people call it a deterministic EM. So instead of having like all these clouds, just say only one this latent unbiased low resolution y prime, but you have to find a good one. And this is basically we'll try to leverage now. In this case, it's easy. Why I mean it's easy? Because you have the physics, right? I mean, you have this high resolution that is high resolution but unbiased, and then you have a biased low resolution. So the one in the middle, the simplest way is just take this one, downsample it as something that has the same resolution as this, but without bias. So basically, in this case, the simplest one, so you have all this setup, just coarsen it, and then you will have your intermediate step. And then in Bayesian, you will say basically this is the mode of the posterior. Now, what it simply does is just have two steps. So you have the first step that you go from a biased low resolution to unbiased low resolution, and then the second step is basically just add resolution. So upscale it, and this is exactly what this is in here. So I won't go into details. So let me see. So how you go from the first step? This is where the math comes in. So the different ways to do this one-to-one correspondence. What we chose here is optimal transport, which has theoretical guarantees. You have scalable optimization algorithms, and also the advantage is like it's really connected to a plethora of GenAI methodologies. So basically, what we want to do is you have a distance. You want a map that takes one of these and move it in a minimal way to y prime, such that the marginals they remain constant. So you have you find the smallest modification such that the probabilities densities at each stage are constant. This is key. I mean, you can prove. I mean, no, well, prove. It's not a theorem, but you can show that this is the minimal requirement if you want to do this properly at the distributional sense. So if you're more familiar in applied math, this is basically a distribution matching type of problem. Now for the second step, this is easy. So people have done this many, many times. So you go from quarter solution to half solution. In this case, given that you chose your samples, you can do supervised learning. So you take one of these, you downsample it, and of course, if the downsample is coarse enough or it's aggressive enough, there's no one-to-one correspondence. So you basically need a generative model or a distributional probabilistic version to go back. And I mean, this is done. I mean, this is well studied. I mean, diffusion models, they do this very well, and you're able to sample things from the posterior in many different ways. And I mean, I don't know, I just show you this. I don't know how many times have you seen this dog in this meeting. No, I mean, every time that I go to summer school in diffusion models, you see this dog at least 5 times. Anyway, so you have more details here if you want to go. I mean, I gave a summer school 2 years ago. That in retrospective now looks very outdated, but it's still the basics are there. And so that's kind of the main point. Like this, you have 2 steps. One is a distribution matching. So you try to basically move the sample in the correct distribution using optimal transfer tool. And the second is just it's a more, I mean, vanilla super resolution step. And I mean, it's a sample. So you get this is the input, different coarsening levels. And of course, I mean, this went to NeurEPS, so you have to test it with everything that is under the sun. So this is our result here. And you can see that basically we obtain most of the large scale features, and it looks similar to a true sample. So here you don't have ground truth because again, there's no pairing. So there's not like an input that has an exact output for the true sample because of the chaotic behavior of the problem. Now, what it works better than other methods, there's 2 main points here. One is like using the optimal transport, you're able to model the full multivariate. So if you go back to techniques used in weather and climate, most of these problems, they do univariate. So basically you have 1 pixel, you have like a sort of distribution, and you try to fix the distribution to that pixel, and you do that for every pixel. In this case, you try to do the full stuff, the full snapshot with all the, I don't remember, like a few thousand degrees of freedom at once. This will help. And the others allows you to maintain spatial temporal patterns, which is very important for weather and climate. Because at the end of the day, a hurricane is something that goes in space and time. Flooding event, space and time, and so on. So just to recap, how this works, you have y prime, transformation tries to put things in the correct order, and then you have an invert downsampling that is just a super resolution step. Now, okay, the question then becomes like how you go from the y to the y prime. In this case, I just use like a very blunt tool that is optimal transport. Optimization, just put it there, run it, it's fine. But in general, like in real life, you do have more information. You have physics. You have like a statistical tooling in the sense that you have correlations that you want to impose, and so on. So how do we do this in a more systematic fashion? Particularly when you do this on actually weather and climate problems. So we have 3 quick examples. So the first one is what they call ensemble forecasting. So this is basically you have an initial condition, you wiggle a little bit, and then you want to basically generate the ensemble after that. So this is bread and butter for hurricane forecast. You have your position, you wiggle a little bit, and you let it run and see what the hurricane is going to go. The point is this is very expensive, particularly if you want to run this for like a month or so on. So the question is there any way to make this cheaper? And the answer is yes. So you still do, instead of trying to run all the samples at once, you will do is to leverage the fact that you can run these simulations, but just a few. So in this case, your one prime here is basically one or two trajectories of your system. Let's say x1 and x2, and then you can do conditional sampling. So you will sample x based on this x and 1. So you just simulate 2, and then you build the rest of the ensemble just by running a generative AI tool. In this case, it's a diffusion model. And why this helps? Because basically what you want to capture is the likelihood of having this extreme event. And when you have extreme event, you need to samples, enough samples to capture the full distribution. So this is a heat wave in Portugal in 2022. So this is the temperature that was observed. And these in the squares are the full operational ensemble. So you have a few members. So you can see that it's very hard to basically capture the likelihood of this star. But if you are you just run like these two squares, and then you use this methodology to basically generate the full ensemble, you can basically compute the likelihood of this little star. And this is basically what this is telling you. So if you use this technology, you can have much lower price score, which is basically a measure of how well you can capture that extreme event. So this case is the same idea as before. The difference is that we use Y prime instead of using the optimal transport, which is just a simulation to help us. Now, you can run the same thing for what's called downscaling. So downscaling is the same feature as before. So you have a simulation that is very low resolution, and then you basically want to have something that is much higher resolution. Why? Because typical climate models run a very, very coarse, like 100 kilometers, 150 kilometers, but people care about something that is like around 25 or 9 kilometers. So if you want to run this with traditional methods, so you will do is basically, you have the full Earth, you basically take a patch, and then you run a high resolution model inside that patch, and then you take that one and write an even higher resolution in a smaller patch, and then you have this cascading effect. So you have different resolutions. So in this case, what we can do is use one step of this cascading as a latent variable, and then do the rest with a generative AI tool. So again, this is the same thing as here. This Y, what we're changing is basically how we compute the T. So in this case, is you leverage the fact that you have a regional climate model, so only works for example, in the west of the US, as a stepping stone to generate things that is even higher resolution. And why is that? Because this step is very cheap. This step, if you want to run simulations, becomes very, very expensive very, very quickly. So here we change the most expensive step by a generative AI tool, a diffusion model. And what this allows to do is basically capture the physics much better. So this is Santana winds that are the main contributing factor to wildfires in LA. So if this is a thing is like 2080 or something like that, that's a prediction. So this is our target. So this is basically the index. So this is the winds, and this is the fire index. And you can see if you have like a regular model, everything seems to be very, very homogeneous. You don't capture the full certainty, and then you don't capture, for example, the Channel Island. You don't capture the fact that it can get fire. So basically, you have a strong wind enough. Actually, you can the ashes can jump to the island, and something that traditional models are not able to capture. If you do these two steps methodology, so first is just a regular regional climate model plus a diffusion model, you're able to capture this uncertainty much more efficiently. And this basically two things, like you can see the uncertainty in the wind, and you can see the different uncertainties on the Channel Island. Okay. But this is a little bit cheating because you suppose that you have already like a climate simulator. There's low resolution, there's cheap to do, but you still have one. In this case, can you go even further? Can't you just go from just climate simulation that has nothing to do with anything else with something that looks like weather? So basically, go from something that looks like this to something that look like that. And again, this has the same issues before. So from the same period, things kind of have the same statistics, but they don't match day to day. So if you were to do exact matching day by day, hour by hour, that doesn't exist. So how do you basically try to merge these two together? And the second part, in this case, is the phenomenon in here that they don't, there are phenomena in here, tropical cyclones, for example, that people really care for hurricanes, that they basically don't exist in the climate simulation because it's too coarse. So how you can basically generate these tropical cyclones that people care very much from climate simulation that has the correct statistics. Now, this is the same diagram as before. So what you do is have the same point. You have something that is low resolution, is biased, something that is high resolution, unbiased, and then you will do this kind of like a roundabout. So you're gonna go something that is low resolution but unbiased, and then you will jump, you do two-step jump. This is exactly the same as before, the same overall philosophy, just the tools change quite a lot. So in this case, you can go from this y to y prime. The method that we try and work the best is using a rectified flow. That seems to be the one that allows you to go from one distribution to another one in the most stable way. Particularly in this case, as you will, I won't present today. This one was on the other presentation. You do have time. You have a climate shift, so you need to be somehow resilient to shift in the distributions. You have that. Then you will take a sample, like a patch. For example, here is the conus. And in this case, you will basically run a diffusion model for super resolution. So you will get from here to here by running exactly that. So global debias first, and then a super resolution step. So why we care about all of this is because if you do this in this way, you can basically capture tropical cyclones that people have, it's kind of like, it's been the holy grail trying to get a tropical cyclone from climate simulations. And the only way to do this is used to be run very, very expensive regional climate simulations. And why is that? There's two reasons. You need very fine physics resolutions to basically capture these things. And the other problem is that tropical cyclones are very localized, but they travel very, very, very far. So if you want to capture the full evolution, you need a very, very big domain with a very, very high resolution mesh. And the other things, like there's not that many tropical cyclones in the data. I think for a decade you have only 80, or for a decade you have around 80 tropical cyclones. So it's very weak signal to basically to be able to capture. But anyway, using this methodology, you can actually capture these things. And then I think that is, if you're interested, links to the paper and to the code submissions. They ask you to release all the code, so you have all there. You have the data. It's about like 100 terabytes of data. So feel free. You have a hard drive big enough to take a look at that. Now the dessert. So slightly good time. So far we try to see learning this type of, to a degree, try to learn things trajectory-wise. So you have a trajectory here, you have a trajectory. Can you match it at some degree? But the point is that usually it's very hard to match trajectories. Why? Basically, we have this divergent. The trajectories diverge very quickly because of the chaotic. Because the underlying is you have a chaotic system. So if you want to do long horizon, they either blow up or they become unphysical very, very quickly. So we tried some success, but the point here is like perhaps you don't need to really go trajectory by trajectory, right? What you may want to do is basically just compute the statistics. So if you have a flow, you know that it's going to be chaotic. Well, you have a flow here, you have an airplane here, you know that it's going to be chaotic. You just want to be sure that whatever you produce here, the impact here has a statistics that the wings don't break. So how do you want that? So how do you go for the full characterization? And again, the point here is like try to exploit these latent structures in the media. So that's basically what we want to do. Now, why they work so well? So they have a few things here. So there's a underlying dichotomy between everything that I said, or not, well, a few things that I said. One, most of these things are you have a deterministic simulation, and for some reason we take like a diffusion model that has a probabilistic description, and we try to put them together. So the question for us was like, how do we merge these two in a way that's coherent? And the way that is when we're drawing this is basically trying to see what is the behavior of the systems when you, for example, increase the Lipschitz constant. So what I mean with this you can have, for example, a very toy problem, so something that just like a line that basically does like a few teeth. And then you can have, for example, this delta that can count for, let's say, like a real numbers. As you increase it, basically these things become it becomes much more oscillatory as we decrease this delta. So you can think this is basically you have a fluid and you either increase the time step or you increase the resolution or you increase the real numbers. And if you were to use a deterministic problem, so if the Lipschitz constant is small-ish, you basically capture very well. But you start to increase, well, decrease delta, therefore increasing the Lipschitz constant, you start to have this phenomenon that the resulting problem basically collapses to the mean, to the conditional mean. And this is what people have observed so far from the statistical description. But this happens for the fully deterministic description as well. But if you were to do the same with a diffusion model at some point, it captures this quasi-deterministic behavior very well, and then have a transition that goes from quasi-deterministic to fully probabilistic. And we have a formal statement. So this is the theorem. So I mean, you can read it if you want, but in English or like in a layman English, like if the underlying probability measure under the continuous stochastic system exists, so we suppose that an underlying distribution, the denoiser of the optimal trained diffusion model converges as the discretization increases. In this case, the random numbers increases, and you'll recover the underlying measure. So basically what I want to mean with this is like, is there an underlying probability measure that is injected from the data? The diffusion model will capture that, of course, up to certain error given by the Wasserstein distance between these metrics, sorry, these distributions. And actually we saw this, we see this in an experiment. So this is the Taylor vortex screens. So the ground truth, this is a sample, conditional sample from I don't know, like T something, I don't remember. And if you do a diffusion model, you're basically able to capture the statistics very, very well. If you do anything that is deterministic, basically you collapse to the conditional mean. And then you can do this you can see the evolution. So when the Taylor green vortex is almost deterministic, or it's because it's deterministic, and then becomes turbulent, and we're able basically to capture this transition because of the power of the of learning the underlying distribution. And can I go down with? And I'm running time, so just like a few thoughts. So I believe that it's a very exciting time for inventing new ways of computing and doing science. The main issue is that this is very fast. So you can see that every time you have, you go to NERSC, you have 28,000 papers. You go for the science track, and it's like 5,000 papers you have to read and digest and try to come up with an idea. So this is like it's a really, really fast. It's still nascent. So there's a lot of unknown ways that this can work, different points of how to handle these things. And there's a lot of also different paradigms. So you could see like neural operators, like pins started like 2 years, then got neural operators, then people like forgot about that, then went to a probabilistic model, people forgot about diffusion models, now rectify flows or so on. So this is going to be very, very fast. And the main point is like there's opportunities to advance all this research with new challenges as they arise. Main things, how to incorporate physical priors into statistical modeling choices. So this is basically the underlying point of all this talk is how to add these physics priors to a statistical modeling and how to make it marry both in a way that is performant. And the point like how to generate statistical output that are physically possible. So this is very, very important. You can see per images, but the idea is like you do have the correct statistics. And I think like the most important issue is like how to reduce the sample complexity. So for all these things, you need a vast amount of data. And if you look at the applications that have been successful, weather and data, for example, it have a massive amount of data that's been performed like and cured by people before. So, for example, in weather, you have like around 7 petabytes of data. So you need this large amount of data to make these like the recent innovations that have really been successful. So the point here, like how you reduce that to a point that is more feasible. And again, thanks to my collaborators, and thank you very much.
So we can take a couple of questions and between people and lunch, but.
Yeah. So there's two things, right? One, so how coarse and how badly your simulation can be. So there's two things, right? One, I mean, if you go back a few years ago, people were trying to add all these closure models, in which they start with something that is very bad, and basically what they did is enhance the numerical solver. Didn't really learn the new distribution, something new. So from us, you can go. I mean, it depends on your setup. For fluid, for CFD, we go for something like finite differences that we know that is very, very bad. And we go out on like a 64 cube, and then we go to spectral elements with this hyper viscosity, and we'll go to 56 cube. So that's kind of the jump that we can make, and that's fine. Again, you're not looking for doing trajectory by trajectory. You're looking to do statistics. So it's a different, easier problem, but it's more well suited for this type of generative AI. For the climate, that's a completely different story. So we go from 150 kilometer, something that is completely, I mean, if there's climate scientists, I don't want to offend them, but I don't know how they do it. It's non-physical, you have like factors everywhere. So I'm not sure how the physics goes. And then you go to weather, that is 25 kilometers resolution, which much more better physics, much better description of the phenomenon, and with data simulation. So we'll go from there to the other. So, I mean, I don't know how to quantify that. But did I answer your question? Yes.
Okay, we'll just take one more. And then, you're around for
Yeah, I will be around. Going back and, well, we'll see the traffic. Okay, so that's a good question. So the one point, like that's why we use like a probabilistic model. So what is the idea is like it will give you the posterior that has the possible answers. Now, how you know the conditional is the correct one? A priori you don't know. So that's why we, I mean, in the second part of the when we in certain cases you can actually build ensembles and be sure that you have the conditional, and that you can test it. Yeah, I mean, okay. We account for that. We, in general, we don't measure, we don't, we don't benchmark that particular side. So what we could do is basically run an ensemble, things that produce similar stuff in a delta T in which you have some variability, but not enough to be completely different. You downsample all of those, they look very the same, and you train on those. What we found is that, I mean, for some kind of dark magic that we don't understand yet, that the diffusion model trained on one sample actually reproduces fairly well the conditional distribution. We don't know why, and I think that nobody does, but that's what we observed.
Right. Well, let's thank you again.